Good morning, everybody. This is Dr. Halappa Gajera, Department of Electronics, University of Mysore, Karnataka, India. Today I am here to present our work, Design of Rectangular Microstrip Antenna with a Defected Path Surface for Improved Cross-Polarized Radiations. My co-authors are Kaushik Datta, Purnima S, Chandrasekhar K.S. and Chandrama. My contents are as follows. First, introduction, primary objectives, earlier investigations, proposed antenna, simulation and experimental results, conclusion, and finally references. As per the introduction of microstrip patch antenna, we all know that it is very simple and very popular antenna. It consists of three main parts. First one is ground plane. Above the ground plane there is a substrate, and above substrate there is another metallic conductor that is called patch. When it is excited properly with a suitable mode, it will resonate at a particular frequency. There are various feeding techniques which are available. First one is coaxial profile, strip fed, aperture fed, and gap coupled fed. Like that, there are various feeding techniques. And this microstrip patch antenna is very popular because of its small size, lightweight, low cost, easy to fabricate, and it can be easily integrated with MMIC, MIC technology. It may be available with various shapes like rectangular, square, triangular, circular, semicircular, etc. And it also supports both linear as well as circular polarization. It also having some demerits such as low gain, narrow bandwidth, low efficiency, low power handling capacity, and it has high cross-polarized radiations, which is undesirable for some specific applications like satellite and other communication applications. The objective of our work is to minimize the cross-polarized radiations by using some defected microstrip surface technique. We are considering probe-fed microstrip patch antenna. There is a huge cross-pole, particularly in probe-fed microstrip patch antenna, because of this vertical probe, which will also behave like a monopole radiator, and it will provide monopole-like radiation in all directions as I shown in the red arrows. So this will be the main source for the orthogonal component. These orthogonal components are the source of cross-polarized radiation. Along with this, the probe-fed microstrip patch antenna, which will resonate at a particular frequency, that is the estimated frequency. Along with that, there may be chances of exciting higher order modes, as I shown here. This M2, this is the higher mode along with the dominant mode. Due to this mode, the radiations of the dominant mode will be affected, particularly in the cross-polarized radiation characteristics. We intended to suppress XP radiation by using some DMS technique. So, if you go through the literature, there are so many investigations are already reported. First one, you see the rectangular microstrip antenna with a defected path surface for miniaturization and improved polarization purity. In this work, they have also etched some arc-shaped slot cutting at the radiating edges. By that way, they have achieved only 14 dB radiation XP suppression, and they achieved around 25 dB isolation. And they didn't discuss about the what is the reason behind this. And in the next paper, you can see there is also some slot loading technique, but by this way, they have achieved only 21 to 30 dB isolation, but they achieve some impedance bandwidth due to shorting of the patch and the ground plane. And in the third work, you can see there also some microstrip defect they have used, but they achieved only 23 to 35 dB isolation, not the XP suppression. XP suppression is very less. But in these works, what we found that the resonating frequency will be shifted because of the loading of these slots and cuttings. Okay, but in our work, the resonating frequency is fixed, and also we are going to eliminate the higher mode. That is the main thing what we achieved. Our proposed antenna looks like this. This is the conventional patch antenna, which will resonate at 3.1 gigahertz. But when we place the defects on the surface of the patch, two symmetrical lambda by 4 dipole like structure we cut on the we etched in the surface of the patch, and it is symmetrically placed very close to the profeed. By this way, what it will do, it will suppress the orthogonal component along with the radiations created by the profeed. By that way, it is going to suppress the cross-polarized radiation of the patch. So this is the desired copole current pattern, but here it is orthogonal component as we explained. That is due to maybe probe or maybe higher order mode. Okay, these will be suppressed automatically. We are enhancing the radiations in the H plane. This is the S11 characteristics comparison. The black one shows it is the resonate conventional microstrip patch antenna, which is resonating at the 3.1 gigahertz. Along with the dominant mode, there is a higher order mode. This higher order mode is the main source for the cross polarized radiation. If you see in the dotted red line, the dominant mode is no alter in that. In the same frequency we are getting, but it is somewhat minimum, S11 minimum, because of slot loading, but it is totally eliminating the higher mode. That is the beauty of this work. Okay, what is the benefit from this? Just see the radiation characteristics. We have considered only H plane radiation. We didn't bother about the E plane radiations because E plane copole as well as cross pole radiations are unaltered due to this technique. And normally E plane cross pole is very low, below 50 dB. I think we have to concentrate only on H plane. H plane, the cross pole is the important parameter that should be controlled. Here you see the block lines, that is conventional microstrip patch antenna. Copole, no change in the copole, but in cross pole we are getting only 15 dB in a conventional patch. If you calculate the isolation 15 plus 6, 21 dB we are getting. By the proposed technique, see, copolarized radiation does not affect in this dotted red line. If you see here, the cross pole is drastically reduced. It is around 48 dB. The total isolation is more than 50 dB. 53 dB we are achieving over the wide band, wide range, plus or minus 180 degree. This is the achievement of this work. So the dimensions of the slot are optimized for getting the optimum design to implement the prototypes. This is the work which we have done, that is by varying the slot width and the slot length, what are the changes with respect to H plane radiations that we observed, and we decided some particular dimension for the optimum design. Then the experimental setup, this is the conventional prototype we fabricated, and this is the proposed prototype, and this is the S11 characteristics measurement setup, and this is radiation characteristics measurement setup in IISc Bangalore. And we got the experimental result very much similar to our simulated predictions. Just see the comparison here. Measured conventional, proposed conventional S11 parameter, almost 1-to-1 matching here. In the H plane radiations, the proposed as well as conventional paths we have compared, it will perfectly match with the simulation predictions. Finally, the conclusion. What we achieved here, simple technique by etching two slots of optimized dimensions on the surface of the paths. We can control the XP radiations as well as we can eliminate the higher order mode, which is along with the dominant mode. By this way, we are going to control the orthogonal component, field component. By that, in other way, that will enhance the radiations in the H plane, particularly cross pole component. This configuration is so simple and can be adapted for any wireless and mobile applications where we can use the microstrip patch antenna. Along with that, this technique can be easily adapted to any working antennas which are already in the field for the better polarization purity. That is the beauty of our concept. And finally, these are the reference work we have referred. And thank you and all. Thank you.